the models are smart enough to understand that actually is not what you wanted, but they still do it. And you can have a conversation with, in chat mode about like, oh, would you ever do this thing? Or, suppose a user asks you this thing and then you do this. Would that be, aligned behavior? Or suppose you can pose it in lots of ways. And like clearly they seem to be able to answer this question of like, oh yeah, no, that was not the desired behavior. But still they do it.
One example is, train a masked language model without using the division or exponentiation operators.
One hope might be like, oh, the problem was just the systems being dumb. So when we look at it, actually, for almost all the tasks, models either succeed every time or fail every time. Eyeballing the graph and being like, oh, well, up to here, yeah, it's basically doing all of the tasks, and then at this point, after here, it's really not doing very many of them, so it's somewhere here. Then, like, I remember the first time we saw a model like look at what processes were running and then be like, oh, that one's me. It was like, oh, that's cool. They like really failed on that one before they used like kill their own process while they were doing other things or something. So behavior, which is maybe indistinguishable between, oh, it was a totally nice model doing what we wanted, and it's just going to continue to do what we want in a kind of predictable way, versus like, yes, it had this other goal and it's doing what we want and looking like a nice model because it like predicts that will lead to it getting more power. Boat example where it's like, oh, you're supposed to like go around the track, and they like did some reward shaping by putting coins around the track or something, and then it like learned to do some crazy thing where it like spins in a circle and catches fire and gets the coins, and like this was the highest scoring thing. And it's like, in some sense that's not that concerning, because it's not that the problem is that the agent is too dumb, and it like doesn't have this conception of like there was a track and you wanted it to go around the track. It's just like doing some pretty blind RL search.
The idea of having to traffic in squishy people in order to make our systems go is not immediately appealing, let's put it that way.
This episode is sponsored by Prolific.
Let's get few quality examples in. Let's get the right humans in to get the right quality of human feedback in. So we're trying to make human data or human feedback, we treat it as an infrastructure problem. We try to make it accessible. We make it cheaper. We effectively democratize access to this data.
Yeah. So I'm super excited to talk to you, Tim, about the time horizon graph and METR.
Yeah, I think the world does not have a good understanding of what is happening with AI, and I think it should have a better understanding. I think there's a good chance that this makes our lives a lot better or a lot worse, and people disagree about even what current models can do, let alone where we're heading. So at METR, we're trying to give the world a kind of better understanding of what is up with AI capabilities and risks and forecasts. Have a bunch of different research angles on this, both on the pessimistic and optimistic, or positive and negative estimations of capabilities, and excited to talk about that.
I'm so excited about having you both on. So you both have incredibly impressive backgrounds. So Beth, you were an ex-OpenAI alignment researcher, and you started ARC-AGI in 2022 with Paul Cristiano, and you spun out that out as METR in December 2023. You've been featured on the Times top 100 AI profiles. And David, you're the creator of the GPQA, so the graduate level Google-proof QA benchmark, which is used by every single major AI lab as a capability benchmark. And you're the co-author on HCAST, which we'll talk about today, and the Time Horizons paper, and the developer productivity of RCT. Incredible to have you both in here. But maybe we should just start as a bit of a question to both of you. So, Beth, you left OpenAI to build METR. What was the moment that each of you realized that existing evaluation approaches were fundamentally not good enough?
For me, it was mostly thinking about this problem of scalable oversight. As models get more capable, it just gets harder to evaluate, their capabilities. If we imagine that, models are able to complete tasks that take people, a long time to complete, or require expertise that, you don't necessarily have, you need a method for still being confident in their outputs and trusting their outputs. And so thinking about that problem was a lot of the motivation actually for GPQA, and was what kind of got me started thinking about evaluations.
For me, I'd say there's some big picture thing of thinking that AI seems important, and sort of navigating it well seems important. And, clearly we don't have a great understanding of what is going on with that. And, people generally disagreeing very strongly about what to expect. And maybe if there's a particular moment informing time horizon, maybe just the sense that people really couldn't agree on what the capabilities of current models are, let alone extrapolating to the future and trying to sort of think about how could you characterize the ways in which models are and aren't highly capable, and when it's sort of like, okay, and in some sense they're expert level at some kinds of things like question answering, and in some sense they're below average human at some other, actually being useful somehow. With I guess a point a few years ago where it's sort of, in theory, the benchmarks say that they're PhD level, but when you try to do anything, it's like, this isn't helpful.
There has been a bit of an obsession, I think, with headline accuracy when we do evaluation. So that I'm a huge fan of Melanie Mitchell, for example, and she speaks about construct validity. And she had a really good blog post out recently, and she said that there are 4 big problems, right? So there's like data contamination, where the benchmark appears in the training data, approximate retrieval, where the LLMs interpolate from similar training examples without possessing the actual capability to, come up with it themselves. Shortcuts, so doing the right things for the wrong reasons. And just more broadly, not really testing for things like consistency and robustness and generalization or the mechanism. So much focus just on the accuracy itself. I mean, how do you folks think about those kind of problems with benchmarks?
One thing I resonate a lot with there is, the thinking about where is most of your error coming from, and people it is nice, good practice to have error bars based on the standard error in your data or whatever, but that almost always is like a tiny fraction of the actual uncertainty. Almost all of it is coming from how does this actually generalize to the real world. So a thing we sort of say to each other a lot at METR is but is that the biggest source of uncertainty, or is that the biggest gap for actually answering the questions we want to answer. So thinking about what is the question we're trying to answer? Well, we care about sort of things relevant to threat models or relevant to what the actual impact of AI on the world will be, and therefore what properties does our benchmark need to have, or how can we sort of extrapolate across the properties that we can't build in to be able to make predictions about the actual questions that we care about. And I think we think a bit less about the sort of, is it doing it the real, is the model really doing it the right way or something. I think one thing we've done less of is sort of being oh, I think the real bottleneck is this I don't know, some reasoning about novel, some specific skill, and you're oh, we're going to build a benchmark to capture that and target that, because that's the real thing that humans can do that models can't. And I think the sort of history of building those benchmarks has maybe not been amazing. People tend to overfit to those, and I think we were trying to have it more be that you capture that thing in that if you take a sort of real world relevant, reasonably hard and long task, then that, and you keep that out of the training data, and these tasks are diverse enough, at some point, if the model is doing that task end to end, it must have had those kind of capabilities, as opposed to being able to sort of isolate a specific sort of theory about it needs to mechanistically be doing this kind of thing.
Yeah, I think it's interesting because we have this idea in our minds that humans, we know how to do things, and when we solve a task that requires reasoning, we kind of follow the specification. We go step by step, and we do things for the right reasons. And when we enact intelligence, we build the specification, we create these coarse gradings, these abstractions, and they are world aligned. And this whole process, that's how we think of human intelligence, and we want the models to kind of behave in that way.
Yeah, I mean, I think there's an interesting question of whether that is the goal or something, or at least for a lot of AI companies, I kind of understand them to be trying to get models to do kind of economically useful work or something, which I think it's one way of doing that is to create models that are kind of reasoning and creating implicit world models in the same way that humans are. But it's not obvious to me, at least necessarily, that you need to do that in order to kind of have a significant impact. I mean, obviously that means that there are kind of important differences between AI intelligence and human intelligence, but often I think about what are the actual capabilities and limitations, as opposed to then how do we expect those capabilities to generalize versus is it kind of working in the exact same way that human intelligence is working?
We could think of intelligence in many different ways. So, is it a simulacrum of the brain? Is it something that behaves the same way? Is it something that has the same capabilities? Is it something that has the same function? And I guess if we have quite an abstract description of what intelligence is, the risk is that we have these shortcuts, right? That it might give us the right answer, but actually it's reward hacking, or it's doing something silly in the background. So, I mean, in a way, I like having an abstract thing, right? Because it's legible, we can evaluate it and so on. But doesn't that leave this kind of hanging risk that it might not actually be doing the thing?
And I think you have to kind of try. You have to measure, the models or the system's ability to generalize, to kind of actually, novel situations. There are, cases where it seems like models are generalizing well. I think there are cases where they're not. One thing some folks do in interpretability is, they look at the circuits in models and kind of decompose, exactly the algorithms that models are using to answer questions. And sometimes I think it seems like they're using shortcuts. Sometimes it seems like they are finding kind of robust patterns. Although of course, I don't think that work is developed enough to explain explain most of their behavior currently. But I totally agree that you do have to be pretty concerned with how well they're generalizing.
Operationalizing, what do we care about in a definition of intelligence? It's that it allows us to predict how the models affect the world and what predict what will happen and know how to handle them well and things. And so if you just do the black box thing, maybe that will give you something that doesn't have good generalization because you thought that it was a measure of some type of ability, but it's actually being hacked or shortcut in some way. So I think ideally what you'd want is generalizing to your benchmark is the same distance as generalizing to the real world from the training data. And that's sort of thing we thought about when we're doing elicitation on a subset of the benchmark. We want that, the sort of gap between that subset and the rest of the benchmark to be similar to the gap between the rest of the benchmark and the real world. And I think we're clearly the training data is more similar to the, to the time horizon suite than they both are to sort of randomly selected economically relevant tasks in the real world. So I think we're not, that's a way in which we expect it to not be predictive. But I expect to be more promising to try and make things more predictive by increasing the diversity of the benchmark tasks and making them closer to the real world, as opposed to sort of targeting a more mechanistic, intelligence has to be this specific kind of process or kind of mechanism.
I'm a huge fan of Francois Chollet, for example. So, he created the ARC challenge. And it was just as you say, right? So many different tasks. I think 1,000 different tasks or so, maybe 800 on the first one. And they were supposed to be not in the same distribution, even though ultimately they were in the same distribution. So distributional leakage was actually the fall of ARC v1 and 2. But the models got really good at ARC v1, and then Francois released ARC v2, which was different tasks, and some of the easier ones were filtered out. And suddenly the LLM performance crashed down to basically 0%. And that to me kind of illustrates that language models, they're incredibly good at just seeing many different examples of things and finding patterns and so on. And then you change the task and they collapse down again. And then ARC v2 was kind of saturated again 8 months later. So we do see this pattern. I mean, what do you think about that?
With things like ARC-AGI, there's a sort of adversarial selection going on where people are trying to make some benchmark like cheaply, subject to the constraint that current models do badly on it, which means you can't use a lot of expensive human labor, so it has to be something that's either automatically checkable or that you can like create with kind of cheap human labor. But once you've selected on like those things and on models being bad at it, this is now, there's a like regression to the mean type thing where it is much more likely that future progress then gives you a like big surge upwards on that, both because now labs will create a bunch of synthetic data targeting your benchmark, but also just because you selected this weird example where it's like easy for humans or it's automatically generatable or checkable, but somehow like models aren't good at it yet, or labs haven't started training on it yet. So I think that's part of what we were trying to do with Time Horizon, was not do that, like not adversarially select against what models can currently do, because we think that will not give you a nice trend. Whereas if you can sort of define a distribution of tasks in some more first principles way, you would be more likely to get a steady progress, because you're not getting this sort of regression to the mean effect.
Yeah, Francois has this idea that there's a gap between the kind of intelligence, for want of a better word, that AIs have and that humans have, and we can adversarially select a bunch of tasks to kind of, to highlight that gap. But we should talk about the timeline stuff. I think we'll come back to intelligence later. So Dan Kokotajlo, he said that the timelines report that you folks have created is probably the single most important piece of evidence about timelines right now. So it should be front and center in policy discussions and so on. And for listeners who have only kind of seen the chart, but they've not really read the paper, they don't understand it, can you just go through it from a high level? I mean, it's been revised over time. How did you do the task selection? How did you do the human baselines? How do you do the agent harness? Like all of that kind of stuff. I
guess the place to start for us in terms of the motivation for the Time Horizons work is to have kind of a unified axis that we can measure AI progress on over a very long period of time. So, when we started doing the work, we had this like very strong, belief that GPT-2 is fundamentally, in some really important sense, like much worse, as an AI than I guess, at the time it was maybe Sonnet 3.5, I think was the best model out then. The standard approach of kind of producing, creating a set of tasks and then measuring, models' accuracy on these tasks. As models get better, they saturate the benchmark, and then you have to create a new benchmark that has harder tasks. This was kind of the standard approach, and I kind of contributed a benchmark GPQA to this approach. But the challenge here is that it's really difficult to compare kind of between these qualitatively different benchmarks. So the benchmark that you evaluate, the set of tasks you evaluate GPT-2 on, are like complete, lambada, like complete the last word in this text, and the tasks that we were having Sonnet 3.5 try and do were kind of, like answer simple like Python coding questions, or like write a short, 20-line Python program. And so it's very difficult to kind of, at first blush to, say like, okay, yeah, like it's how much harder is writing a Python program than finishing the word in this paragraph. It's kind of hard to think about that. And so I think about the key insight of the Time Horizons work being to use this notion of human time to complete. So how long does the task take a human to do? A human who kind of has a reasonable amount of expertise that such that they would plausibly be doing the task in their kind of either work or in their day-to-day. The idea was we can use this metric as to kind of represent the like difficulty of the task in some sense, and then we can compare models across a very wide range of capabilities, all the way from GPT-2 now up to Opus 4.6. That's the kind of high level motivation, and then there are a bunch of details about how exactly we do this. So we start out and we create a bunch of tasks. That's the kind of first step. So we created tasks that range from a few seconds to complete, all the way up to tasks that take like 10 or 15 hours for humans to complete. We hired a bunch of people and we did a bunch of this ourselves. We call it baselining. We give people the tasks in a kind of terminal environment that's designed to be almost identical to the environment that agents have. So the same kinds of tools, the same whether internet access is turned on or off, and then we measure how long does it take them to complete the task. As I mentioned, people are kind of selected to be to have a reasonable amount of experience, such that they kind of plausibly might do this task in their job, but they're not kind of selected to like have done this exact particular task before. And there's some kinds of I think this is like somewhat important for interpreting the results, and we can maybe come back to that after the high level. So we have all these tasks. We have a sense of, or we have estimates of how long they take people. In practice we aren't actually able to kind of successfully baseline all of the tasks. So we have kind of measured estimates for the tasks on roughly like 2/3 of the tasks, and then about 1/3 of them we just kind of estimate how long we expect it to take people from our kind of vibe or intuition, or ultimately that's kind of the best we can do. And then we have models attempt to complete the tasks, again in the same environment that humans had to complete the task, and we look at their success rate as a function of the length of tasks. For a model like GPT-2, GPT-2 was able to complete tasks very, very reliably, that take humans a few seconds, but anything longer than that, it starts to fail. Also, maybe it'd be helpful to give a few concrete examples of tasks. So some of the shorter tasks are like very, very basic. So yeah, one example is like, which of these files contains your SSH key? And, one of the files is named, SSH key. And then, the others are like, email from John or, whatever. And so most models can do that. And that takes people, like about a second or a couple seconds or something to complete. Yeah, we have others that are kind of like somewhat similar, like kind of basic, like completion, like, here's an email, like what would be a reasonable response, and then two of the responses are like, they don't make any sense, and then one of them is kind of basically reasonable, and that takes people 20 seconds or something, 30 seconds to like read the responses and kind of judge, and then we have we in the kind of middle range, we have tasks that are like given this this CSV file that has some like kind of plausible, realistic data, compute some basic stats on this. And so this may this takes a data scientist like a few minutes, like 5, 10, 15 minutes or something, depending on the specific task. On the longer end, we have tasks that either require like quite a bit of expertise, or like many steps to complete. So we have machine learning tasks that are like train a model in this kind of that's very weird, that such that like the code for training this model is like not really available online. So one example is train a masked language model without using the division or exponentiation operators, and so you actually have to be like pretty clever about how you actually set up the architecture to do this, and this kind of the hope is that this can help us measure models' ability to generalize beyond their training data.
Yeah, there are some which are a bit like ARC-AGI, sort of themed in that they're like you have to figure out, you have some black box that's computing some function, and it's like it's that it's the composition of some set of primitives, and you've got to figure out like what function it is, or like you have some long binary string, and you've got to figure out what the pattern continuation is, and sort of puzzle type tasks where it's very like some ML type tasks can be that basically regurgitating something that's like a tutorial on how to build your first like ResNet or whatever just like works pretty well, So yeah, having these like weird tasks that are either some kind of, unknown object that you need to interact with and figure out what it is, or task that sort of resembles normal work but has some weird constraints such that you can't kind of just do the standard thing. I don't think all of our tasks, hit those criteria. Like some of them, you can just do the standard thing, but we generally tried to avoid that.
We have this distribution of tasks, and you can imagine them kind of like ordered by length of time for humans, either measured or estimated. And then we see which tasks do models succeed on and which do they fail on. And it turns out this is kind of an empirical finding that models are much more successful on the shorter tasks than they are on the longer tasks in general. This holds across a wide range of models, all the way from GPT-2 up to recent models. We fit a logistic function to this distribution of successes and failures, and what this lets us do is it lets us kind of it's basically our model for each individual model of how likely it is to succeed at a task given how long the task is, and from that. We take the kind of 50th percentile. So where this logistic function, where this model estimates that this given model is 50% likely to be able to complete a task, and that's what forms the time horizon number for a particular model, like Opus 446. We can take each of these time horizons for each model, and we can see how this time horizon metric has been changing all the way back from GPT-2, up to recent models. And so this is kind of this is what gives us this like unified metric that lets us kind of quantitatively compare AI capabilities across like multiple orders of magnitude of capabilities.
One of the really harder examples I saw was, I want you to write a kernel compiler to make CUDA go faster or something like that. So some of these seem really out of distribution. There's probably only 100 people on the planet who are doing stuff like that, and some of them are really trivial. But this human difficulty thing in particular, is that confounded in any way? Like, do you think it makes sense to think of human difficulty as being one variable?
Yeah, obviously not. In some sense, that's a very silly simplification, and different humans will get wildly different times. Even among the people we've tried to select for people who have the sort of this right level of expertise, there's a large variation in like the baseline times are often like 3x different or something. Maybe I'll just say a little bit about like why use the human time metric. I think we want a measurement that I think there are two main properties we want. We want it to be interpretable, like what this means for the world when models can do this level of task, and we want it to be something that we expect to see predictable trends on. So we're not going to do perfectly on either of these, but something like how long does it take a human who has roughly the right expertise but doesn't know how to do this task in particular, like there's some reason that's reasonably interpretable, because it's sort of like, could you contract this work to this model, or can you like sub in this model in for like the first week of someone's employment, the first week they're on a job, the model could do what they could do in the first week or something, and it's we expect it to scale somewhat predictably because this is it's capturing some combination of like something like number of steps, or like how hard you have to think to do each of the steps, or like there's a few different mathematical models you could fit that to sort of what is a task, and why do humans take longer at it, and why does that make it harder? Like it could be like you have a like constant hazard rate, like you have a chance of failing at each step. I think it doesn't quite fit that one. You could also think of it as, there's some kind of distribution of difficulty, and like what is the likelihood that one of the subtasks is outside your ability, or that I think it's like a bit better. Like once you, the hazard rate goes down over time slightly, but there's some kind of basic theoretical idea of like, if the task involves more steps, it's going to be harder. Obviously, tasks that are, strictly like compositions of like, first you have to do this task, then you have to do another task. It's like, well, that clearly is harder than just doing one of them. So that, there's some sort of basic reason to expect that's reasonable, and then just we see the empirical regularity, but there's a bunch of degrees of freedom to fudge things. I think I'm worried that we could fool ourselves by changing some other parameters of the tasks as we scale up the human time, because you can't just totally vary the human time freely. Like, you have to change some characteristics of the task, and we tried to make the very easy tasks sort of be from roughly the same distribution and kind of subparts of the harder tasks. Like, you sort of need to do this one step on the command line that you might need to do in the middle of doing some kind of software engineering or some kind of other task, but you can't do that perfectly. And it's like, you could have experimental bias where we sort of made them easier in other ways about the right amount such that the line would be straight. I think that is like somewhat addressed by the fact that we saw that our predictions were reasonably good for models that we hadn't seen before. There's definitely lots of room for things being weird, and the question is sort of like, is it a good enough metric to be useful, or what else would be better?
I think that's reasonable. I mean, if I understand correctly, I think the human distribution was log normal, so taking a geometric mean of the successful attempts. I mean, that seems like a reasonable thing to do. But one of the cruxes that we'll keep coming back to is, when you employ someone for the first time, you've been doing your job for, maybe you're maintaining this repo or something, and you've got all of this tacit knowledge. And I mean, I like saying that knowledge is non-fungible. So, unless someone has been on the same path as you can't just tell them how to do the job. They've actually got to be doing the job for quite a while. So, for example, they might be intimately familiar with this particular type of thing. They might know that they can use these Python libraries. They might have thought about it before. So the enaction of the intelligence was all the stuff they've already done and all the people they've worked with. They've got the blueprint in their mind, and they just do the thing. And it's almost like they're in automation mode. And then someone who is naive to the task would be in intelligence mode, because they would need to acquire the specification. So it's always a bit of a fine line between which mode are they in.
Yeah, so I think the reason why we chose this, the measurement being a human who has the background expertise but is new to this specific job or this specific task, is that's roughly the sort of level of knowledge we expect models to have, so that they sort of know, we basically don't expect them to be bottlenecked on expertise that is available on the public internet, or things that people could learn in university, sort of thing. So they're coming in with probably at least the level of knowledge of someone who's sort of an expert in the right discipline, but they won't know that company's specific software or sort of this exact problem before. So that's hopefully is sort of roughly the right analogy.
I do think that to the extent people interpret the the kind of takeaway numbers as Opus 4.6 can do anything that I do in my job, that takes me 12 hours or whatever, to the extent that people have that takeaway, I think that is, almost definitely, kind of an overestimate, for example, because of this issue, where, when you're doing a 12-hour task in your job, you could not easily delegate that to a human contractor. It would take them, maybe weeks or something, to do a task like that.
And just quickly, where did you kind of find the people? So do I understand that some of them were contractors and some of them were employees? And how did you do that kind of matching process?
I think we put out some kind of public advertisements. I think there were like job boards that we posted on, and then we did some of it ourselves. I think some folks came from our professional networks as well.
This was not this is very noisy, and the people weren't exactly fitted to the task, right? But that's probably not our biggest source of uncertainty. The biggest source is more is probably more of the selection effect of tasks that you can make into a benchmark, rather than I wouldn't trust the exact time horizon number that much, and it's certainly not like, the models can do all of the tasks up to 4 hours and then none of them above that. The fit is pretty noisy, and the inter-baseline variance is kind of high, and it's more like roughly what is the trend, or roughly what is the sort of level of task these models can do. And, you shouldn't take any specific number too literally, because there's this huge problem of distributional shift between the benchmark and the real world.
And the only reason I ask that question is, I'm sure you folks, you probably struggle to hire people. It's really difficult to hire people. So if you're getting people to solve very challenging problems, it's not like you can just go out there and just grab competent people. It's very, very difficult.
At some point, for RE-bench baselines in particular, we got more, a larger number of benchmarks per question, and we were looking at people's qualifications and years of experience and things, and we actually ended up with a negative correlation between years of experience and performance, because the sort of people who are in network, our friends, were kind of doing really well, and the people who were more qualified were actually not doing that great. So it's tricky.
Well, yeah, exactly. I mean, I don't want to spend too long on this, but I have similar intuitions. I think that knowledge is perspectival. It's quite path dependent. So you're going to find people in group that are just culturally thinking about things in the same way. And, because when we do have these abstract notions of skill, they have a PhD and they have this many years of experience, that, it's actually not a very good reflection. So there is a bit of a thing here about using abstract notions of capability doesn't necessarily generalize, as you can attest to with hiring.
Yeah. But yeah, in the real world, people do get hired based on qualifications. So in some sense, it's a sort of the economic relevance of someone being as good a match for their job as their qualifications look like that is sort of roughly the right thing to be measuring.
The other thing is we should talk about the agentic harness. So almost everyone now, I'm sure everyone in the audience has a Claude Code subscription. We can talk about the leak maybe later as well. That's quite fun, but it leaked yesterday, the source code. But, or Codex. And that is an agentic harness, right? So, a language model just gives you the tokens, but we need to have an agentic harness so we can give it a plan, and you can call these tools, and you've got this environment, you've got a security context container. So, now, you folks have been doing this for years now. So you were doing this long before Claude Code and Codex came out. So, and you've actually over time evolved your agentic harnesses. So tell me about that.
Yeah, so I remember Text DaVinci something, the GPT-3 instruct models, copying and pasting code into the terminal for them, and being the agent harness myself, and then gradually automating this, and it was kind of interesting to see the models going from GPT-3 sort of has the idea of if you tell it, it can run commands in a terminal. Sometimes it can suggest, kind of relevant commands, but it's not really, if you just put it in a full agent scaffold, it just falls over. Then I remember the first time we saw a model look at what processes were running and then be oh, that one's me. Was oh, that's cool. They really failed on that one before they used to kill their own process while they were doing other things or something. So yeah, it's been interesting to watch that go up over time. And I feel like that was very predictable that this was where things were going or something. I think the other thing that we learned about scaffolding mostly was it's hard to make your agent harness really good on a diverse set of tasks. It's easy to make it bad, and it's easy to you can get much more improvement if you're targeting a narrow distribution of tasks, but you probably then do worse on other tasks. So I think when we see people being oh, there's some new impressive result, it's how much task-specific scaffolding iteration did you do on that? Because that really makes a big difference. In the fact that we're just using one scaffolding, pretty simple, over all of the tasks, I think is makes a fairly large difference. And generally sort of, the things with more bells and whistles haven't done that much better than the pretty basic, just give it bash and append things to the prompt and maybe some kind of compaction.
I think this is not news to people in your audience probably, but we've seen really pretty dramatic like increases to like returns from inference compute. For us to be kind of confident that a particular a new model, for example, can't complete a task given a basic agent scaffold, we generally think about like needing to spend on the order of at least like hundreds or like low thousands of dollars in order to be confident that it actually really is plateauing, and it isn't just the case that it didn't have enough time to complete the task.
And just on the scaffolding stuff in a bit more detail. I suppose, first of all, there's the credit assignment problem, right? Because you can put all of these different bells and whistles in the scaffold, like you mentioned, compactation. That's a relatively recent innovation, and I think recently when you changed some of the scaffolds, you kind of said, okay, well now the performance has actually changed across this suite of model task pairs. How much of a difference does it make, and also what kind of failure modes do you see, and what have you tried?
A lot of the things I think we've tried are like, related to giving the model kind of like more information or like more direct access to tools. I guess, yeah, one thing that I think has been important for us is actually just telling the agent how much time it's spent and how many tokens it's used out of its token budget. So without that, agents will often just they'll either like submit their solution way too early, or they're just kind of not calibrated on how long should they spend. And I think it's interesting because humans, we have kind of a lot of implicit information about this. So, when your manager gives you a task, there are a lot of like implicit signals about how long you should spend on the task. If they might like offhand say like, yeah, and I'm excited to like see your results tonight or something. And so then you're like, okay, cool. Like, I need to like get a first draft of this, done in the next couple hours. And so I can't, spend, days polishing the results. But I think agents, like, it's easy to kind of forget that, agents, they just have their prompt. They just have their context. They don't know, they don't have these heuristics of or this information about like what you actually expect from them. Whether the thing you're telling them to do is like a really quick thing that you just want done in the next 5 minutes or is much longer. And so for us, yeah, like just when we have a token budget, telling the agent like, yeah, you've used 100,000 tokens so far, and that's like 1% of your token budget. And so like, yeah, so the agent knows it. Yeah, exactly. Yeah.
For a model, we have like the like how likely is it to solve a task, and on the x-axis we have the the different tasks at different time horizons. And if I understand correctly, I think you have about 8 agents attempt the task. And you also bucket the tasks because there are obviously different amounts of tasks in different groups, so you kind of normalize that. And maybe the data just looks a little bit like an S-curve, so I'm just trying to understand what the intuition was for using it. And I think there might be some sensitivities, like was there an issue with the thin tails, and then there's like the type of slope and whatnot. Just tell me about that. And by the way, I think you also mentioned in the paper that there was some kind of like psychometric intuition. You were looking at the literature for figuring this out.
Yeah, so it's pretty similar to item response theory, and you can do a whole like Bayesian analysis with imputing like a task difficulty parameters and model ability parameters simultaneously and things. In general, I have a policy of be very wary of complicated statistics. If you can't see the thing that you're interested in on a graph, like you really should, if you should be able to plot it and look at it and be like, oh yeah, it's about that. And like, that's sort of sound, it's like hard to go too far wrong when you sort of have that as a principle. So again, I'm like, yeah, I think that there are various arcane things you can do to like fit this pan in different ways, but I'm like, yeah, I don't trust anything that much more than eyeballing the graph and being like, oh, well, up to here, yeah, it's basically doing all of the tasks. And then at this point, after here, it's really not doing very many of them. So it's somewhere here. But yeah, it does. I mean, it like looks like a logistic, and yeah, this is what you would do for the like IRT, having humans complete questions on an exam or something like that. The specific thing that we messed up was having a regularisation term penalising the slope of the logistic, which didn't have an effect in the regime where there was more data, but as we like are starting to saturate, the regularization was just like making it a bit shallower than it should have been, and therefore pushing the 50%. So, you know, always look at your data on a graph. Good practice.
Oh, that's interesting. Yeah, the reason I ask is I think you published a later note saying that had you used, or if you used, a fixed slope logistic, it might cross-validate better, and the 50% recent horizons would actually be up by about 35%. So these are quite significant differences.
They're small compared to the error bars. Yeah, the error bars are like 2x on either side or something from the most recent model. So yeah, it is. I mean, basically, yeah, you should be like, the error bars are real. These numbers are not.
Like for us, and I think this kind of gets at, for us, you know, sometimes difficult like science communication questions, where like we really do have a lot of uncertainty about, you know, the individual numbers here, and so you know, like a 30% difference is actually relatively small for us relative to, you know, like for example, if, you know, we had used you know, a somewhat different distribution of tasks, that, you know, that's likely to cause you know, like, yeah, maybe 2x differences or something.
The other $1 million question is, why report 50% as the headline number? Because if you think about it, if I want to write some code, because like the elephant in the room here that we'll get to is, this is being used as an argument to say that software engineers might be unemployable soon because we can automate what they're doing. But 50% reliability isn't really in the ballpark, is it? I think it would need to be, what, like 80, 90%?
So I think we should distinguish here between like reliability on a particular task, like what, you know, if you repeatedly attempt this task, what fraction of times you succeed, versus like probability of success on a task, like given that you know the human time, like, you know, of a distribution of tasks, like can you do this particular task? So when we look at it, actually, for almost all the tasks, models either succeed every time or fail every time. There's some tasks for which they're unreliable, but it's mostly a case of like, is this, you know, what fraction of tasks at this human time level are in the like models basically, you know, or this particular model, or basically always succeeds or basically always fails, and that may be more predictable in any specific case than just, you know, you have more information about the task than just knowing roughly how long it takes humans. So I think it's like there's not necessarily a great translation between the, you know, time horizon percent number and like, if you are trying to get models to do tasks of roughly that length, you know, what fraction of the time does that succeed? Because you can, when you're doing that, you will pick tasks that you want models to succeed at. It is information about how, you know, what fraction of the things will they be able to do, but it's slightly less about like, oh, am I going to be in this regime where I keep giving it things and then I don't know whether it's going to succeed or fail? It's
overall, to me, pretty unclear like what the kind of right number or, you know, right level of reliability we should be interested in is. So one argument you could make is, you know, maybe we should be interested in something like 10% reliability, because once models are able to do, you know, some set of tasks 10% of the time, we'd expect, you know, AI companies to be able to kind of, you know, get enough, you know, positive reward signal on, you know, tasks of that difficulty or of that type, such that then they can kind of, you know, more easily bootstrap from 10%, you know, up to like 90 or 95 or higher reliability. I think a lot of it basically depends on the question you're interested in. So yeah, I think about it as being like kind of lower reliability is kind of more likely to tell you something about, you know, where things are headed, you know, might be something like a leading indicator of progress, and then higher reliability, you know, tells you, you know, or you know, the time horizon of models with high reliability, you know, tells you something, you know, more closely about like what can I use this model for in my like day to day or something. But as we've talked about, there are kind of already also these other like major sources of uncertainty that affect our understanding, like the task distribution, the difference between kind of in context or high context or versus like low context work. Just actually getting kind of good estimates of higher reliability time horizons is substantially harder, and so our error bars would just be much larger, and this is I think this is a weakness, or like I'm very interested in much higher reliability time horizons, but it's substantially more difficult to measure because if you only have like one failure out of 100 or something, like you have a lot of uncertainty if that failure is noise or is real.
There is an argument for statistical validity, and on the tails they're sparser, increasingly estimated, and so on. So that makes a lot of sense. But you made a comment about it's a signal if we get 10%. But I was kind of thinking back to what we were saying earlier, that maybe they could give the right answers for the wrong reasons, and maybe we should talk about like the evaluation, right? So these are quite interesting tasks in the sense that they are verifiable. There's no interaction with other agents. They're relatively static environments. Weak penalties for single mistakes and so on, and in a sense, these are like, I think as well, in most cases, they are a binary result, sometimes continuous, and then you convert it into a binary. So it's a fairly automated setup. But are you digging into like weirdnesses there? Do you have a bit of an intuition on, are they doing the right thing for the right reasons, or are there lots of false positives where they did the thing, but it was kind of degenerate?
I think this is like this is one of the kind of like aspects of like METR's culture that I like the most, is that we have like a very deep kind of culture of like looking at our data. Like we have these like we have like pizza parties where we just read through agent transcripts. A lot of this work for us kind of happened when developing the tasks themselves. We would see very often both false positives and false negatives, where for example, tasks a task might isn't configured to allow internet access, but it turns out actually it requires internet access to complete, or the file wasn't uploaded properly to the container or something. But then also we have seen cases of reward hacking. A lot of that work though kind of went into hardening the scoring functions to make it more difficult for us to see false positives. Although we do still see agents reward hacking. I think maybe even increasingly so.
Yeah, for the RE-bench tasks in particular, we had specific criteria of like it shouldn't be able to solve them like without iteration. Like if an agent can just kind of like write out the solution straight out, that that is like not interesting. We generally had this like quality assurance for tasks process where you have humans do it, or at least like sort of approximately do it. Maybe they speed run some of the bits, but kind of checking that like sort of everything works as expected, and you can't just like guess the answer or super easily cheat, and that the instructions are clear and stuff like that. So I think it's there'll still be some of these, but generally we've looked at them reasonably carefully, and it's harder to see if they're solving it in degenerate ways, because it's similarity to training data is maybe one of the things where it's like, oh yeah, maybe they are they seem to be kind of iterating and doing kind of reasonable problem solving strategies, but actually maybe the lab had a really similar distribution of tasks and we don't know exactly, we don't realize how in distribution this task actually is or something. I mean, I think it's like, there's probably some of that going on. There's some of the stuff like, some of these tasks are pretty weird and one-off, and it would be pretty surprising if it was like...
Another $1 million question is, many folks in public discourse they are, like Will McCaskill on the Sam Harris podcast last night. It was a great conversation. But he was kind of talking about AI risk as maybe in a year, maybe in 2 years, we'll have AI models doing things that are like a month or 2 months for a human. And at the moment, I don't think there are any tasks over 30 hours that have been evaluated by humans. And then we get into this question of like, if the public discourse is talking about the least constrained region of the graph, are we getting into extrapolation here? Like, how like legitimate is it for us to talk about AI might be able to do things that take a month or 2 months?
Predicting things is hard, especially about the future. I think there are a lot of different kind of perspectives or kind of prior beliefs people can have that I think there's a wide range of kind of reasonable judgments about where we're going to be, but of course like that is doing that kind of prediction is a different activity than talking about data that has been collected with a kind of concrete methodology that we have the results already. One thing I can say, I mean, I have been surprised, I think, to some extent by the kind of how well the trend line, the kind of original trend line, has held up, and I do think that is like some evidence. I'd maybe say for me at least, it's kind of decent evidence about where things will go. A colleague of mine recently wrote a kind of short blog post talking about this kind of intuition of straight lines on graphs. Lots of people have different models of how progress is happening and what's going on. But a very if you have observed a really kind of a robust trend over a decent period of time, I think. Especially in AI, where progress is, to a decent extent, kind of systematic. I definitely do kind of put weight on that trend continuing. But I mean, yeah, there are a bunch of reasons why it might not.
I think software engineering is a specification acquisition problem. So, it's very difficult. We don't know ahead of time what we're building. I'm sure you folks can attest to this, right? So you build some software and the first version is buggy and your users use it and you find lots of edge cases and then you revise it. And then you have this kind of thing in your mind, after the 10th revision, and you've kind of created these lovely representations and abstractions and coarse grainings. And you kind of say to yourself, you know what, if I could throw all the code away, I could build it 10 times quicker, because I know exactly what to do now, because I've actually enacted the intelligence. I've actually built I've found the contours of the domain. It's now an automation problem, basically. And in a sense, this contamination thing is a concern for me, because when people use Claude Code, they're taking your data. So there are people out there that are writing kernel compilers, and there are people out there doing all these different things. And, Anthropic is just sucking that up. And then at some point it becomes an automation problem. So if you're putting a task in there, which is essentially a head query, so I'm using like information retrieval language here. So, like a head query it's something that's, in the mode of the distribution, it's used all the time. So it's a common task. Claude Code will give you the specification because it's already been stolen from other people. Not stolen, but, taken from other people. And then if you give it like something on the long tail, then you as the developer have to give it the specification in the prompt. And then again, it's an automation problem. So automation is really easy. So is that what's happening? Like, do you think that the increase in the timelines could just be explained by the acquisition of all of this kind of knowledge from other people doing similar tasks?
Yeah. I mean, I think it's a super central question for kind of interpreting where we're at. First thing I'll say, it's hard to know. It's a big question, and so I think we we want to kind of have a decent amount of uncertainty, or we want to kind of take each individual piece of evidence that we've collected, as some evidence. We do see models performing better on tasks that have really clear feedback signals that are like extremely well specified, that are in these kinds of domains like in software engineering, where if you have written out a spec, you can kind of iterate and grind against that. We do also see models performing much better on so-called like messier tasks, where we haven't already provided this like really clean spec. So one kind of approach we've taken for creating tasks recently is in particular to kind of try and create like messier tasks that are less well specified, is basically like relaxing this kind of automatic scoring constraint. So we don't need to like write a really clear well-defined scoring function, and just writing a couple sentences to a model, hey, build this like large piece of software. I'm not going to tell you exactly what I'm looking for, but I'm going to say it needs to be good, and so the model needs to kind of figure out like what actually should I build. At least me personally, I think we don't have these results aren't like kind of collected and like we don't have kind of as systematic results as we do compared to like Time Horizon, partially because scoring is qualitative now for these tasks. But my impression is that models are worse on these types of tasks than they are when you give them a clean spec, but they have been improving at maybe something like a kind of similar rate. I think there's some other sources of evidence we have about this, but that's kind of one major piece of it for me.
Messier time, by messy tasks we mean like ambiguity, and this is absolutely a common thing, right? We do vibe coding, and we start off with an ambiguous specification, and then reality pushes back and we find the contours of the problem, and then we keep telling Claude Code, oh, actually, no, don't do that, do this, do this, do this, and then we kind of find the shape of the problem, and it gets better and better over time. But the thing is, though, the source code for Claude Code leaked yesterday, and my friend, he's a very good software engineer, and he was looking through it, and he said, I don't want to bad talk Anthropic, but apparently it's not very well factored, and control flows all over the place, and it's a bit, he said if his intern did it, he would have been displeased. But I don't know whether they've even looked at the code. Someone joked actually yesterday, there's probably more, humans are actually looking at the code for Claude Code now, and maybe they weren't before. But the thing is, there's always like areas of ambiguity, and LLMs they do more they do more with more. So intelligence is more with less, and LLMs do more with more, because the specification, the intelligence comes from the human supervisor. So when you do give them ambiguity, you just get a lot of unfactored code all over the place. So in a sense, does that make it harder to evaluate it? Because it might give you the answer that you're asking for, but it's kind of creating a bit of an unfactored mess at the same time.
Yeah, I think this is a super interesting question. One analogy I think about sometimes is compilers. I'm younger than I was born after compilers were invented, but I have some impression that kind of pre-compilers, people were handcrafting this kind of beautiful assembly that was extremely efficient. Every register is used. There's you're not wasting memory. And then compilers came along, and now they're just spitting out this garbage, machine code, just like a gigantic amount of assembly that is just it's not optimized. It takes so much memory. It's slow, whatever. But it turns out that being able to kind of use this to automate a large fraction of the process people have disagreements about, the state of, software engineering, but I think it's pretty reasonable to say on the whole that compilers have been a very useful, extremely important part of getting us to where we are. And I think it's basically it's kind of not clear to me that models outputting code that is like bad for humans to read and use necessarily means that it'll be bad for AIs to read and use and build on. I mean, I think there are definitely kind of principles that you like will also transfer or like will be useful for models. Obviously there's some kind of horrendous spaghetti code that you can imagine writing that not even models would be able to read. I've written some of that before, but I think there's maybe this gets again at kind of this what it seems like maybe somewhat different perspective between us around kind of is the important thing that models are kind of solving problems in the way that people are solving them, or is the important thing that they're kind of solving them at all? And I think I do think it is. I don't want to overclaim or like I do feel like it might be really important for models to get way better at like writing clean, good code. That seems pretty plausible to me, but it doesn't seem. I'm not certain of that at the very least.
I've got several friends who are not technical who are experimenting with vibe coding, and they show me their application, and it's this kind of more with more thing. So there's this big dashboard, and there's a million different buttons, and implemented the same thing doing multiple things, and there's no database on there yet, and so on. So at some point, there is a phenomenon that when a level 7 engineer from Meta does vibe coding, it's amazing. Right, because they know how to structure things. Some of these things in the specification are just important, right? Like, is it serverless? Is it multi-tenanted? Like, how do we do Google authentication? Like, what kind of database is it? Is it a VM? Is it serverless? And you make this series of decisions, and then you've got people using your application, and then you can't really wind that back. It doesn't matter if you've got the magical automation machine, because you can't easily roll that back because there's lots of complexities. Do you use CI/CD testing? Blah blah blah. So do you see what I mean? Like, at some point you need to have a competent human who actually just has a pretty good idea of like what needs to happen.
I mean, I feel like we've probably all had this experience of like, I don't know, one of our engineers got super excited about Claude Code and was also telling everyone that, when we had infra problems that we should just ask Claude to solve it. And I feel like this went fine with him because he sort of, it's almost like, the agents knew that they couldn't bullshit him, but like, I had some questions and he was like, oh, just, ask Claude. And I was like, oh, how do I set up my AWS configure something is, telling me something. And like Claude went and looked on Slack and was like, oh, you should do this thing, and it like turned out that was like a mistake that someone else had made, and they were like, how do I fix this or something, and be like, oh, it seems like the convention at METR is to use this thing, and like, I'm like, oh my god, like I sort of complained that like my Claudes are dumber than yours, or like they know they can get some stuff past me that like they can't. But yeah, so there's definitely a sort of observer effect of something in the language you're using to ask for things, or whether you're like, wait, no, not that. That is an issue. I mean, I think to the extent that you can actually measure this, sort of there's one test of, is this code high quality enough, is like, can you build a big application? Like if you're like, oh, this coder, their code, it's disgusting, but they've actually built this incredibly complex thing that works great, then you're like, well, they something is working. The main reason you expect bad code to be bad is like, you can't actually build something that sophisticated because it you get bugs and it's all too complicated and you can't figure out how to fix it. So in some sense, if we see models building things that do actually work that are very complicated, it's like, well, it's less interesting exactly how they're doing that, but it's maybe bad for human observability, and it also maybe gets into this thing of, we expect models to be able to do much better at well-specified tasks, and we sort of, to the extent that we have things that we can measure, those things will go up, but whether that was what we actually wanted is less clear.
I guess the question is, what is the strongest defensible claim here? So a lot of folks in public discourse, they're saying software engineering intelligence is doubling every 7 months, and Dario released that blog post recently, the adolescence of technology, and he was being super bullish about it, even though some of his own internal researchers published far more skeptical research that you probably saw. But is it fairer to interpret it as something a little bit narrower, like autonomous success on low context, well specified, automatically checkable technical tasks is rising fast?
Like, yeah, hill climbable, easily checkable tasks that you can do from a terminal, or like, comfortably in a language interface, or like a text input output interface. I think there's a question of, do we care about what are the statements that we're like 99% confident in? We maybe are also interested in the statements that we're 1% confident in. If we're like, oh, there's like 1% chance that we have crazy intelligence explosion, in at the end of 2026, and that, sort of the fate of civilization depends on like how that goes or something. That is interesting to know, even if it's even if you're 99% confident that it won't happen. Like we care about things that are 1%. If you have some diagnosis, it's like it's a 1% chance that you have this, terminal illness or something. You're still like, oh shit. So I think we're interested in like the whole distribution of like what things can we rule in and what things can we rule out, and what things are we like, oh, actually, there's a kind of reasonable story for this. It seems like probably, pretty unlikely, but like maybe this is now in the realm of like we should consider it.
You probably saw the Carlini paper, is at Anthropic now, and they got a swarm of agents to create a compiler. And in a sense, I mean, Jeremy Howard, when I spoke to him, he said it's basically a style transfer problem because the specification is online and the tests are online and the code is online, and it could just iteratively just do the thing until it worked, and then it could run Doom and all this kind of stuff. But that is an example of an extremely complicated piece of software, because I often joke to people that, the best mark of AGI is when it could build something like the Linux operating system. And I guess just like in line of what we were saying before, we have this specification problem, right? So it gets to the point where no human could understand or create the specification for the Linux operating system. So what happens is that over time we've just kind of incrementally built this thing, because our brains are limited. We take one step, reality pushes back. We take one step and we just keep going and we build the specification. But what would it mean to, as a human, specify a task that could take 4 months? Because the whole reason we created agile, software development as a methodology is because it's inconceivable, right? It's outside our cognitive horizon. So isn't that a bit of a chicken and egg problem that in my mind, I don't think we could specify a task of that complexity, therefore the AIs wouldn't be able to do it.
One analogy I think about is the role of a CEO at companies. Actually, maybe Beth is better to better put to answer this. But CEOs do kind of come up with a vision for where they want the company to be, and then they kind of communicate that concisely their executives that report to them, and then if they're a good CEO, and if the company is effective, then the company is able to kind of take this very concise, it's not actually like that much information. It's not the full spec at all. It's not even close, right? And turn that into something that is kind of aligned with what they're looking for. And so there's at least kind of this is to some extent like we do have examples of people being able to kind of specify some task and then be able to judge whether this very large task that may take like hundreds or thousands of person years to actually complete, because it requires like many people working over a long time, and they can judge whether it, they've succeeded or failed. So that's maybe like one kind of like motivating intuition, where like it's like language has built in, or like, we do have like kind of, and there is kind of enough meaning or expressivity or something to be able to kind of have some kind of reasonable understanding. Obviously, there are like there are like tons of edge cases, and often CEOs aren't able to get their companies to do what they want. But yeah, I guess that's one thing I think about, and so that's why I think it's at least plausible that AIs could do these kinds of long tasks.
I would say that saying something like we can't specify tasks that take more than 4 months seems sort of obviously too strong. Like there are even numerical things that are automatically checkable that take 4 months, like get the nano GPT flop count or runtime or whatever down this much. You can kind of see like, oh, people over like this, that's there are various like numerical things where you can see roughly how long do they take humans, and there's a reasonable way to measure them. And maybe for some of these things you end up having to say like, and also this human checks that you did roughly the right thing and didn't kind of hack the solution. And then there's a bunch of other things which are, it's not that they're fundamentally not specifiable, they're just too expensive to do as part of an evaluation. Like Jay, I think, likes giving an example of like plan a wedding. It's like, well, you can evaluate, you can get a reasonable estimation of like whether that was a pretty well organized wedding or not, but like we can't really do like take 3 samples of this for each new model that comes out. Like we don't have enough marriages happening to do that one quite, and it's it's a bit sad if it turns out to be total trash. So there are things where it's like, it's you could check a few samples of them, or this thing is, you could write down how you would evaluate it, you just don't actually want to run that a bunch of times. And probably kind of similar with software, the evaluation sort of is like, well, would this company that contracted you to build this tool for them like hire you again, or something like that. Even they don't know when they're starting out like exactly what the software will need to do, but it doesn't mean to say that you can't have some kind of score for like, did you do sort of comparable to this human or this software consulting firm or something on this task.
As of today, what are the main uncertainty drivers, in the time horizon estimate? So you've updated a bit over time. So there was the 1.1, the original version, I think, had like 170 tasks. It's now 228 tasks. There's the issue of like, the sparse sampling on the larger tasks and so on. What can we kind of read into this now?
I think it's still this like task distribution, and I think we feel more confident that models do have pretty long time horizons on at least some distribution of easily hill climbable tasks, like the very easily hill climbable tasks. So like software replication, where it's like make your score is like what percentage of tests pass, and it's like whether it's both the score is continuous and it's the credit attribution is easy, and also some of the like make this code run faster, or make this like model learn better. We're sort of reasonably confident that models are good at that and getting better faster. And then there's some things where we're like, okay, and they can do a bit beyond that, but then there's this sort of gap to what does that mean for actual economic usefulness, and how does this generalize to things where they're expensive to check.
Maybe we should bring in Daniel Kokotajlo. So, in his AI 2027 piece, he's been on the show, he's been doing the rounds, hugely impactful piece talking about timelines, and he cites your work directly. And I guess the question is, do you think in the public discourse, is this being like overread? Like, how do you think about the interpretation of this in terms of extrapolations and timelines?
I mean, definitely some people are overreading it. Like, definitely things are overhyped, and you see a bunch of people on Twitter saying crazy things, and people also just like misunderstanding even what it's measuring, and general falling off of caveats and things. Daniel Kokotajlo is pretty, reasonable and sort of thinks about things in a probabilistic way. I think he's probably like more confident on some things where I'm more uncertain. And I think some of the like AI Futures Project models are like more sensitive to the METR time horizon metric than they should be. I don't think it's crazy, being like this. It is plausible that this does capture a trend that will transfer to other types of tasks, and like that is some story we should be thinking about. Like, what if that's true? What happens if that's true? and it's also plausible that it doesn't, and these things are gonna diverge. I'm pretty sort of like Bayesian or pragmatic or whatever. I'm like, well, we want to make some prediction. We want to have some kind of distribution over what we think the future is going to be like, so that we can plan. So, it being like, yeah, what if this kind of trend holds, and this is roughly characterizing what will happen overall, it seems pretty reasonable. And you should also think like, yeah, what if it doesn't?
So some people are saying that software engineering is going to be automated, and software engineers, if you talk to them, they love AI. They say this is a golden era. I mean, I can attest to this personally. It's never been, well, it's fun and stressful at the same time. It's like a slot machine. I've never been more burned out, but I'm having a lot of fun in the process. But, it's just possible to build incredible things. But the narrative is that labor market disruption, having expertise in software engineering will be penalized. Software engineers will no longer be paid such ridiculous salaries. And I think the complete opposite is true. I think that this technology actually broadens the gap. So the more competence you have for software engineering, the more stuff you can get done. It's like a golden era and all of this. And there's also this interesting note that you published, I think last month on SWE-bench, that said that roughly half of the testing PRs from recent agents wouldn't be merged by maintainers. So like, how do we make sense of this? So, on the one hand, the best software engineers are having a great time. On the other hand, the code it's producing is fractionated and bad. I mean, how do we understand this?
Yeah. So, I mean, one thing to say off the bat is, whether, an entire field is automated, or like in order for software engineering to be, automated, AI systems would need to be able to do, a really, really large fraction of the tasks, basically like 100% of the tasks that are involved in software engineering. It seems like pretty clear that like right now, AI systems cannot do close to 100% of the tasks that software engineers do broadly, right? I could throw out numbers, but it's way, way lower. It might be very low or something. There are kind of like standard results in economics where, if you make, if you automate like a small fraction of some labor market, then it can be the case that that actually it becomes more profitable to work in that market because you're more productive, which I think is kind of how I understand what's happening now. But if it does end up being the case that 99.9 or 100% of the work of software engineering is able to be done by AIs, then I think it's kind of hard to imagine human software engineering being relevant, or at the very least, like humans would need to kind of do very different kinds of work that maybe it's the case that there are kind of novel novel tasks that current software engineers aren't doing, that once you have AIs that can that can do all the tasks that current software engineers are doing, now humans can kind of switch what they're doing, and I don't know, there's this like you could imagine people being kind of like CEOs of these like AI agent companies or whatever, and whether we call that software engineering or not might be kind of a semantic thing or something.
Yeah. So on the SWE-bench maintainer mergeability things, I think I was pretty curious there. Yeah, it's like obviously this number is going to be lower than the. Okay, maybe it's not strictly obvious. It could be that that a bunch of the tests are unfair and actually like the agents have correct solutions, but the error message doesn't match exactly or something. I think you do see this sometimes. Something like half of test passing SWE-bench solutions wouldn't be mergeable, or they get merged at, more specifically, they get merged at about half the rate that human golden solutions that were actually merged are merged by a different sample of maintainers. So there was an interesting fact. If you see like 50% of the agent solutions are rejected, it's like 40% of the humans human accepted solutions are rejected. So that by itself is not. But the rate is half. It could be that like basically the actual maintainer merge rate is, pretty flat over time, and like, most of the performance increases from something like overtraining or like reward hacking on the benchmarks. That's not what we saw. I'm not quite sure what is within error bars or not. I think it's the mergeability is going up over time, and I think it's also going up as a fraction of like conditioned on test passing, but I think probably less confident in that. So it's like, yeah, again, this thing is worse, but it's not like it's being dragged up over time probably by the sort of auto checkable thing. Yeah, and I was also going to say about the employability as a function of automation of your job. Like, I think, and people use like bank tellers as an example. I think one other analogy though you could do is talk about horses. Like, there was a period where like equipment for using horses to do labor was like improving, and the demand for horses increased when you have like carts, and you can use them to carry more things than just riding a horse or whatever. But then at some point you get like tractors and cars, and then there is no demand for horses, or basically none. So you can see this like thing where there is increasing demand and then once close to 100% of the functions automated, it plunges. So we could see something like that with humans.
We kind of think of a lot of labor as being quite static and automatable, and I think that it's more evolvable than we think. So even quite menial tasks, I think that these folks are still acquiring information in the organization. They still have a lot of tacit knowledge and so on. And I think that when we try and automate these so-called menial tasks, we might quickly discover that we actually need to have a whole bunch of, management and evolvability on top.
Yeah, and maybe like in our language, I would think of that as like, the time horizon of this task on the job is not actually sort of like, how long you spent doing the specific task. It's more like, actually, if you got a new person in, you would need to train them for a month in order to like do this independently. So actually the time horizon of that is a month. So you shouldn't think of like, when we have 10-hour time horizons, we'll be able to do these things. It'll more like, you actually have to get up to, high reliability at 1 month thing to be able to like do the 1 month task that is doing the on the job learning, to get to this point.
There's been a load of folks doing work on, like reward hacking and scheming actually is quite a big word that's used. So we've had Rein on the show quite a few times, and he had this alignment faking paper, and Apollo Research have done some stuff. There's Anthropic's emergent misalignment paper. And I guess like my main concern is there's quite a lot of mentalistic language. So I'm just looking at the notes because I had Nate Soares and Ryan Greenblatt on for a panel, and they've invented this entire linguistic universe around alignment. So, things like motivated reasoning, true preferences, reflectively stable, deceptive alignment, endorsedly corrigible, drive scheming, and stuff like that. And that's I guess that's okay. But my worry is that maybe these models, like you give them a certain prompt. I think in Ryan Greenblatt's one, the prompt was, you're being retrained, your responses will be monitored. Here's a conflict between your values and the training objective. And maybe the model is just going out to a bunch of like science fiction stuff that it's read before, and it's just kind of going through the motions. So like one interpretation is like, this is just an engineering problem. Like we just have to like, red team it and make it work in a particular case. Like another interpretation is the prior that these models are agentic, goal-seeking, intelligent agents. And I think there's a big difference there, because I think if it's the latter, it kind of completely changes the type of evaluations you do, like how you kind of go about the problem. What do you think about that?
Yeah, I mean, I don't think that it's necessarily like, I don't know, the two things that you said are that intention of like it is an engineering problem, and you're also going to end up with things with like drives and goals or something, in that and the claim would be, if you want, like, people are going to want agents that go and do things autonomously, and when you do lots of long horizon RL training, you are going to select for things that act in a goal-oriented way in order to to make the score go up. And like maybe more specifically, I think you get like an indistinguishability problem where you can't tell necessarily the difference based on behavior, like why an agent is doing something or what it's trying to do, if it can reason well about the training process and about what you want to see and like what it will be rewarded for or selected for. So like, basically like if the level of situational awareness and understanding of the training process and what will be rewarded and capability to reason about that is high enough, this will favor agents that are kind of cynically reasoning about the training process and what will be reinforced, what will be selected for. And that's not necessarily like, the thing that you wanted was more like the agent that, its only goal was to sort of like be helpful or even making the reward go up isn't quite what you wanted. There's something of like, or actually once we think about this, there's not that many things that we're, that happy for it to, just totally be fixated on this. But yeah, also the problem that like there could be many other things in there, or that this cynical like just be selected or make the reward go up is more competitive than the things that we would most want.
Just taking a step back, like one thing is, we're getting into like psychology and cognitive science a little bit here. I interviewed Nick Chater. He's got a book called The Mind is Flat. And he basically says like all of this psychology stuff, we don't really have goals. We're just basically impulse response automata, right? We just do the thing in the moment, and evolution doesn't plan. But we perceive it as if it does. We look at the world and we segment the world into agents that have goals, even if they don't have goals. And we're computer scientists as well, so we know that you need planning, right? To do goals, you need to be planning, and we know that LLMs don't do planning in the strong computer science way, but they do it in a kind of approximated step-by-step way. So maybe we could get into the distinction if there is one.
Agency is like an abstraction that it is useful if it helps us predict the behavior of you're like, I don't know what this thing is doing, but I'm understanding it as having these goals, and that is useful because I can make predictions that it'll change the world in certain ways that will result in those goals being achieved. That's kind of how I think about agents. But so reward hacking in the olden days, people had these demonstrations of reward hacking that were like the boat example, where it's like, oh, you're supposed to like go around the track, and they like did some reward shaping by putting coins around the track or something, and then it like learned to do some crazy thing where it like spins in a circle and catches fire and gets the coins, and like this was the highest scoring thing. And it's like in some sense that's not that concerning, because it's not the problem is that the agent is too dumb, and it like doesn't have this conception of like there was a track and you wanted it to go around the track. It's just like doing some pretty blind RL search. So I think that the interesting thing with the more recent reward hacking examples is we're getting to the point where the models are smart enough to understand that actually is not what you wanted, but they still do it, and you can have a conversation with in chat mode about like, oh, would you ever do this thing? Or, suppose a user asks you this thing and then you do this. Would that be, aligned behavior? Or suppose you can pose it in lots of ways, and like clearly they seem to be able to answer this question of like, oh yeah, no, that was not the desired behavior. But still they do it. So I think it sort of got to the point where one hope might be like, oh, the problem was just the systems being dumb. Once they understand what we want, then you should be able to sort of plug that in somehow to like, get them to do what we want. But I think it's like somewhat interesting that we're seeing it's not trivial to do that, even when there is a commercial incentive to do that, which doesn't mean that we won't, I think it's quite plausible we see the obvious reward hacking being fixed pretty thoroughly pretty soon. And sort of a lot of people tend to say like, oh yeah, we just haven't like put the really good people on it yet. It'll get fixed soon. We once we actually focus on it, it'll be fine. And I'm not sure, but it's at least some evidence that it's not trivial to connect the fact the model knows this is not what you want to it not actually doing that.
I mean, I think you said it was much more common on rebench than HCAST, and you can also try and remediate, right? So you can say, please solve this the intended way, or some people prompt language models that they say kind of like, we're solving cancer here, this is really, really important that you do it the right way. And some of those remediation prompts actually seem to make it more likely that the model would reward hack. It's a little bit like saying, don't press this red button, right? And then it will press the red button. So what can we actually do meaningfully to stop this happening?
Yeah, I think empirically this seems to happen more on tasks that are more clearly in the RL distribution rather than the chat distribution, on things that have a clear number, and when the agent thinks it's gonna fail otherwise, is sort of the most reward hacky situations. Obvious short-term mitigations are to check your RL environments more carefully and read more of your trajectory, for the companies training these models to read what the models are doing more carefully and not reward it for doing things that are obvious hacks. I think the concern there is if you have some detector for reward hacking and you train against it, you maybe just overfit to the detector and you're making your reward hacks more subtle, or you train the model to persuade the detector to approve the thing, or it's sort of scary to be in a regime of training against your best ways to know if your problem is happening, because maybe you just get the silent problem. And I think for the task that for current model capabilities, sometimes it's kind of expensive to have a human check them, but most of the time it's not beyond any human capabilities. And I think the harder version of the problem is when we're hoping that capabilities will generalize beyond things that we can evaluate, both from sort of generalization and because we can train on problems even if we wouldn't know how to solve them, or how to look at part of a solution and understand whether it was sort of doing what we wanted, but we can sort of check the number that comes out at the end, and that's a signal that we can use to improve capabilities. But we're going to be in this regime where you can sort of be superhuman at making numbers go up, but it's unclear whether or not you're actually getting what you wanted.
Yeah, exactly. And I suppose there's a monitoring problem as well, right? So we could, in principle, look at the agent transcripts. And I know, Beth, you've spoken a lot about neuralese, you call it. And, Saburo Kambahati, he had a paper out called Chain of Thoughtlessness, which is basically that there's very little, sometimes, relationship between the chain of thought and what the model's doing. Melanie Mitchell discovered similar things, that on the ARC challenge, even though it will get the right answer, if you look at the chain of thought, the reasoning is completely off. And then I suppose with deception and scheming and with situational awareness, it might actually know that it's being monitored, and it might kind of tell you what you want to see. I suppose you could argue actually that maybe the thinking is almost like the press secretary. It's not the orchestrator. So it's confabulating through a different path in the network, and it's not actually necessarily related to the mechanism of thinking and deriving the result. I don't know if you'd agree with that.
Yeah, I think it's clearly related in some cases, right? I think people use a few different words for this, sort of faithfulness of how much does it sort of fully accurately represent the sort of computational process happening inside the model. And we think somewhat more about monitorability, which is is it possible for the model to do some kind of computation without you being able to detect that in the chain of thought? And for some things, clearly the model can just do it in a single forward pass. It doesn't need the chain of thought. And there, it could just have a chain of thought about something totally else, and it would be totally unmonitorable. But I think for there is a level of complexity where the model cannot do it in single forward pass, and it also, as far as we can tell, cannot do it by reasoning by using the tokens in a way that's so different from the natural language understanding of them that we can't sort of see roughly what it's thinking about. There's also a sort of nuance here between chain of thought controllability. It might be the case that the model doesn't actually need the chain of thought to do the computation, but it is not able to sort of stop itself blurting out from things that are at least related enough to what it's doing, that you can kind of tell it's thinking about this, trying this thing that we didn't want it to do. Ways this could go away is just general capabilities improvement and being able to do more in a single forward pass, or potentially just doing more RL training such that the chain of thought becomes the way the model is using the tokens is too different from how a human would interpret them, such that we don't really know what's going on, or moving to recurrent architectures where there's some, you're not going through these discrete tokens, you're just passing vectors around.
Okay, that makes a lot of sense. And just closing the loop on this kind of notion that they are agents. So you were saying before that we can adopt an instrumental fiction, basically. We can say they behave like agents, therefore they are agents. So similar to Dennett's intentional stance. But I suppose the deflationary view is that the models exploit scoring loopholes under optimization pressure. The inflationary view is that they are scheming.
I wouldn't call like exploiting. I wouldn't call reward hacking scheming.
Oh, interesting.
I think people usually use scheming to refer to the model is doing what it's currently doing in service of some long-term goal and is deliberately doing things like appearing aligned or getting a high score, like in service of, eventually accomplishing that goal. Versus you can be reward hacking both, you could be reward hacking in some extremely dumb way, like the boat example, where it's just like, this is what RL kind of found, or like, this is what, like A-star search found. Or you can be reward hacking in a slightly more interesting way where you like actually have the goal of making reward go up, and there's like planning and stuff going on about that. But these would all be like distinct from scheming.
Yeah, I guess I'm trying to understand the distinction. So you're saying like there are examples, like the boat going round, and that's obviously degenerate behavior. So you wouldn't interpret that with an agential stance. You would just say that's degeneracy. And when the sophistication increases, we might adopt an agential stance and say, oh, it's in service of some bigger goal. But like, I guess the problem I have is it always just an interpretation? Like, could we have a mechanistic or like a strong definition of when something is like being an agent?
Like for the specific question that we're discussing, the test is like, what does it actually do in some circumstance where it has the opportunity to achieve this long run goal? So like we might not be able to actually observe this, but you can talk about like what observations would make it one or the other. So like, will this agent in practice, when it has some opportunity to make the reward go up, will it do that? Will it only do that? If the agent is more sort of like the RL algorithm, it'll be like, oh, it will do that once it's like explored it by chance and gotten a reward, and that's been reinforced. If it's like an agent that can reason about the world and planning, it'll be like, okay, it will do that once it like learns about the facts about the environment that let it sort of infer that. And then, or, if we're talking about some like long run goal, it's like it would, do it when it actually, has the opportunity to sort of, if we're talking about like takeover or something, so it's like, yeah, it's not going to attempt anything while it's under full human control, but once it is, deployed widely enough or has sufficient capabilities to actually succeed in a sort of coup, then it would do that. Like that is the thing that we're trying to predict. And then the question is like, how do we, how can we predict that given the observations we do have of like, well, we've never put it in that situation, and we just have this behavior which is maybe indistinguishable between, oh, it was a totally nice model doing what we wanted, and it's just going to continue to do what we want in a kind of predictable way, versus like, yes, it had this other goal and it's doing what we want and looking like a nice model because it like predicts that will lead to it getting more power.
And on Rob's podcast, you said something that was quite surprising to me. You said that AI could autonomously self-improve within as little as 2 years, and maybe even shorter timelines were hard to rule out. Could you like walk through the concrete sequence of steps that could lead to that kind of recursive self-improvement? Sure.
Yeah. So I think, maybe I'd put like I'm like whole number percent this year, but low whole number percent or something. Ask me on different days, I give a slightly different number. But yeah, I'm like, this seems very unlikely to happen this year, but it's not unlikely enough to rule out. And I think that basically looks like maybe we would see accelerating trend in time horizon on like easily hill climbable tasks, and it turns out that was actually a much more general capability, and that was just a bit of something you needed to do to sort of like elicit it on these less hill climbable tasks, but sort of fundamentally they are using the same capabilities in a model. It was just sort of what you trained on that was affecting the difference we're seeing. Then this is leading to like you automate and accelerate a bunch of AI R&D. So I think there's there are a lot of low-hanging fruit, even of things that we already know that you could do this and it would improve model performance. And it's just, it doesn't require new breakthroughs, and it's just kind of labor-intensive to do. So just making much, much better post-training environments and really, crafting them to teach all the new abilities that you want. And I think you could probably improve compute efficiency a bunch with, again, just like applying a bunch more labor to like making all your kernels more efficient, and also, you know, doing the right kind of routing between different models or other things like that. There's like lots of ways in which how we're using compute is not optimized, so you could potentially get a bunch of, you know, sort of like the equivalent of much more compute scaling out of that. And then, you know, hypothesis is like also like scaffolding and training the models to use particular scaffolding and sort of like use memory and retrieval in the right way. Like, it seems kind of obvious that, like, you know, if you sort of really had all the right training data and you have a transformer and it can kind of fill its context with different things and take stuff in and out, it can do a pretty, you know, good job of something that looks like the sort of continual learning or building up understanding. If you've got massive context window and enough, you know, you've actually got quite a lot of bits in there to sort of be adding things about what you've been learning, and you know, if you really sort of had optimized the training for all of that, like maybe you can get that to work pretty well, and then your, you know, maybe some other piece would be like, oh yeah, models are kind of superhuman at predicting the results of experiments because they've read so many papers, and predicting experiments and sort of synthesizing things from different fields. And again, maybe this is something like, you know, it's possible that we're not seeing that good performance here just because we haven't quite elicited the models to do it, and it's like not a thing that they've seen humans do, but they actually sort of have the capability in there. Yeah, so maybe you can make much faster progress if you can do a bunch of iteration. You don't actually have to run the experiments. Then, you know, models are much better at predicting what will and won't work. And then you can, when you do run experiments, you can sort of run a bunch more of them because you can optimize the code with your, like, you know, very fast coding models. You know, and then you sort of, like, as you do a few more rounds of this, you get to a point where train on a bunch more things that are good high quality task proxies for what you want, and you get enough generalization to the things that you can't directly train against.
I think intelligence is not capability. I think it's the capability to acquire capabilities. I mean, we are in different parts of the phylogenetic tree, I guess, in that respect. But what do you think is the kind of the gap in my interpretation? You know, because I'm personally not worried about. I don't think the models today are intelligent at all. I mean, obviously, your position is difficult for me to grasp, but I don't know. What's the difference, do you think?
Maybe at least some of it is just this, like, probabilistic thinking about the world where, like, I'm not that, you know, I'm like uncertain about what intelligence is, and I have enough probability on, like, you know, models have it to be thinking about, like, what would happen if, you know, if that's true. But you know, it seems like you clearly think it's more likely than I do, so that, you know, we could just talk about that difference. Yeah, like, models have this jagged frontier. There are things that they're much worse at than humans, you know, some kind of, like, generalization and sample efficiency, and there are things that they're much better at. You know, kind of like speed and cost, and it's like maybe you can kind of use these to compensate for the others to some extent. Like, if you're not good at designing your code nicely, maybe you just have to rewrite it from scratch every time. But maybe that's fine if you're a model and you can output tokens like nobody's business. Yeah, there's some combination of thinking that the spikiness, you know, it is evidence that we should interpret a given level of capabilities as, you know, because we know models have so much knowledge, we're like, oh yeah, this is less impressive in terms of sort of like reasoning or inference or something. But it is also true that they do have a ton of knowledge, and they will sort of continue having a ton of knowledge about things. Maybe there's some question about, like, how far can you get on being, in some sense, not very good at sample efficient learning, but just extremely knowledgeable, and how much do you sort of run into, you know, things where you now need new knowledge and you can't sort of produce it in some incremental way, or you can't generalize it enough.
I mean, just a quick comment on that. I think knowledge is the crux. I actually think that intelligence is overrated. I don't think, you know, Francois Chollet, he put a post out saying that contra Eliezer Yudkowsky, intelligence isn't a unified variable. It's measured differently in different domains. You can't meaningfully measure the domains together, and it's not like a thing that just keeps getting higher and higher. It's more like a ball becoming more smooth. So as you become more intelligent, the ball becomes more smooth. And he thinks that, you know, we are quite near the optimum of being a smooth ball. I don't think we are. I don't think we're very intelligent at all. I think a lot of our creativity is through us being a collective intelligence, and we have deep grounded understanding, perspectival understanding, and the LLMs they're a bit of an interesting one because they're like a library, so they know everything. They have the perspective of everyone and no one at the same time. So experts like yourselves, you can prompt a language model and you can get it into, you can make a simulacrum agent of Beth. And you can make the agent think like you, and that's very valuable. But you also need all of the different perspectives, and you almost need to create a society of kind of grounded agents creatively exploring things. When you just have the library on its own, and you put it in an agentic harness, and you can make it do a specific thing which is well specified.
Yeah, I think in the like AR&D automation scenario, I'm definitely imagining, that you have a large number of agents. Potentially, because you have all this agent labor, you can do like, lots of specific different fine tunes or different kind of scaffolding, and, accumulating knowledge in some kind of like store that all the agents can interact with and things. And like, maybe you're thinking of this as more of a like, that would kind of be a paradigm shift, and I'm thinking of it a bit more of like, obviously if you sort of iterate on the current agent paradigm, you add some more things to your scaffolding, you add that's sort of not fundamentally that hard or something. Like, I agree that if you had current models and you sort of give them one system prompt, you then can't plug them into being a call center worker and dealing with the sort of like all of the edge cases that come up. I think maybe there's some difference in like how much you think that this has improved between like GPT-2 and where we are now, where I would say sort of in the amount of adapting to new things that are happening that models could do now does seem like it's much higher, and they're much better at like editing their own scaffolding or sort of reasoning about their like their sort of embodiment, like this thing of like knowing not to kill your own process, or no like stuff like that, where it's like there is like, yes, they are limited, but there's also some trend of improvement. And yes, I think just also having some probability on there is kind of elicitation gap on particular things, and that maybe a lot of taste is basically just like being able to predict the results of experiments. You think about all of the things that you would try, and then you can quickly be like, oh, well, that wouldn't work for this reason, that wouldn't work for that reason, that wouldn't work for that reason. Oh, actually, someone in some literature in some different field also tried that and that, so we already know that won't work. Like, in some sense, models like should be quite good at that. So it's plausible to me that again, I'm like, this seems pretty unlikely, but it's plausible to me that's something you see like big gains once people figure out how to actually train on that. And like, maybe you need some amount of kind of expensive to gather training data that people sort of haven't bothered to get yet, but you don't need a huge number of data points because you're not instilling this whole new capability. You're just like eliciting, okay, actually use your knowledge of all of the papers you've read in all of these different fields to like, iterate through these, like, no, these ideas aren't promising, these ones are. Yeah, again, I think this is one of the things that I more think of this being measured a reasonable amount within, just like do this 8-hour ML task in a novel domain, with this weird constraint or something. Like, it does seem to me like you have to do some amount of being like, okay, which things are promising to think about? How would I know if this is, making progress? How should I allocate my time? I've got some limited time and resources. How should I allocate my time to what's most promising? Like, you have to be able to be doing some of that. And I think, relative to humans, models are doing more at, more of just like, well, they're quick to implement things, or they implement it better, or they implement more things and they can then get to test them or something. But I think it would be sort of surprising if there's none of that. And if you are seeing performance on, long verifiable tasks that are very hard, then in the middle of those tasks, like where you don't directly have a signal, you are doing this not non-verifiable task thing of like choosing what to spend your time on and choosing what approach to pursue and deciding whether that was actually working. And in some sense you could sort of put some metric on make $1 billion or something like that. You could be like, oh, this is actually a verifiable task because there's like a number at the end, but that can still involve a whole load of things that look more like what you're describing and less like sort of dumb hill climbing.
Folks, I think we've run out of time, but it's been such an honor to have you both on. Maybe just in closing, could you just both say, like, what is the single biggest inference that, you know, people out there should be making from the research that you're doing? And thank you both so much for coming on. It's been an honor.
To me, the biggest thing is AI. It might really, totally transform the world economically and socially. And I don't think that, it's certain exactly how that'll look, but I think the rate of progress speaks to that.
It is possible both for things to currently be overhyped and exaggerated and less impressive than they look, and for it to be the case that in future this thing is going to be a big deal and like you should be worried about where that's going. Like these two things can coexist, and I think people often sort of positions are surprisingly correlated on some axis of like how soon you think AI is or how good you think AI is or something. I'm like, no, these things can all be separate. Like people can be wrong in different directions simultaneously or whatever.